Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I will introduce the concept of a one-factor analysis of variance, or also known as ANOVA. And it's important to remember as we go through these slides for ANOVA that ANOVA is really just a special case of linear regression. And in this case, simple linear regression. So keep that in mind as we progress through, and you will see the similarities between ANOVA and regression as we progress. When we want to use one-factor ANOVA is in a research scenario where we have a categorical predictor variable and some numeric or continuous outcome variable. So thus far, we have really only talked about analyses for a continuous predictor or a continuous outcome. And we've talked a little bit about how we might switch an interpretation of a regression coefficient that's a continuous predictor on a continuous outcome so that it's categorical. ANOVA provides us this framework for really specifically looking at these categorical predictors. So when we talk about one factor ANOVA, one factor means just one predictor, one categorical predictor, and you've been introduced to that terminology when we are creating factors in R. We know that they're just categorical predictor variables. So some prototypical ANOVA applications, we do see ANOVA is used pretty commonly in certain types of social sciences research areas. So some appropriate research questions that could be answered with ANOVA. One example would be, do three treatments, a therapy, a drug, or a combination of therapy and drug, differentially impact depression? And in this case, the predictor would be a treatment condition that would have the three categories, and the outcome would be a depression numeric scale. Another research question that would be answered using ANOVA would be, do college freshmen and seniors differ in their stress levels? In this case, the predictor would be year in college, either freshman or senior, and the outcome would be stress numeric scale. And then the third question would be, does a hormone replacement therapy produce performance differences on a memory task relative to a placebo? In this case, our predictor has the two categories, it's hormone replacement therapy or a placebo, and the outcome would be a numeric number of errors. So this would be a count variable. So we can return to this smoking cessation study. If we ask a slightly different question, we can use the ANOVA framework. So let's say that our researcher is still interested in smoking cessation, and we are, for our outcomes, still going to have participants record the number of cigarettes that they've smoked per day during the last week. But we want to see if we can influence that number of cigarettes, and so we are going to randomly assign participants to try one of three different quit methods. This is our predictor in this example. So the three different quit methods are going to be financial incentive strategy, a nicotine replacement therapy, or no help at all, just going cold turkey and trying to quit without any aid. So we've got a single predictor variable, which is quit method, and we've got three categories in this single predictor variable. So let's talk a little bit about how we would structure this study. So if the quit methods are differentially effective, that is to say, if we can influence our outcome by creating these three categories of quit methods to see how they differentially impact participants, then our observations are no longer coming from the same population. And this is because we have influenced that outcome by assigning our participants these quit methods. So now each quit method is going to potentially define a distinct population that's going to have a unique mean. That's to say that if we randomly assign participants to these conditions, we can now assume that they do not come from the same population. We're creating these populations that they fall into based on the different quit methods. And the ANOVA model is how we mathematically describe a single score from any of these populations. So our hypotheses are, we're now going to return to group differences. All right, so a lot of times in ANOVA, because we have categorical predictors, we are interested in seeing how the grouping predictor variable, how the groups differ on the outcome. So we're returning to the null hypothesis sort of group differences style of the null hypothesis and the alternate hypothesis. So the null hypothesis here would be that the group means are identical, all right? And let's say that we have J number of groups. In this example, J is equal to 3, the 3 different types of quit methods, all right? So we're saying that the group means are identical on the outcome, all right? All observations are from the same population. That's to say that we are not creating 3 distinct populations. The means would be identical across because all observations are from the same population. And the alternate hypothesis would be that at least 2 of the groups form distinct populations. Okay, so now the alternate hypothesis is referring to group differences, but because we're testing this overall model with a predictor on the outcome and we have more than 2 groups, the alternate hypothesis for the overall model now becomes that at least 2 of those groups are going to have significantly different means. Another way to think about that is that we can also think about this as being a predictor influencing an outcome. And so we can think about this in the same way as regression, in that the explanatory variable, or the predictor, is exerting some influence on the outcome. Okay, so we can think about it in terms of predictor influencing outcome or group differences on the outcome. Group differences being coded as the categorical predictor. So in terms of partitioning variability, ANOVA is actually more explicit in how it divides the total variability. And so we talked about this in regression when we looked at SPSS output, and we saw in the ANOVA table, we did talk about the partitioning of variability and how we would use that to calculate R-square. It's the same for ANOVA, okay? So ANOVA is dividing the total variability into 2 sources, the variation that's due to the predictor and the variation that's left over, right? The leftover error variation. So just as we've talked about in the regression framework, we're going to use the sums of squares and the variances to quantify the size of those partitions. And then generally for a statistical significance test, even if the group means are identical in the overall population, we know that the sample means will still differ somewhat just due to random sampling error. And so with ANOVA, we're going to use that F statistic, that overall model statistic we talked about in regression. It's the same statistic to determine whether the variance that's attributable to the predictor does represent a reliable, replicable effect. That is to say, the F statistic will tell us whether our predictor is significantly influencing our outcome, just as it did in regression. Okay, so next up, we've introduced the smoking example in these slides, and we've kind of covered some of the general bases of what we're going to look at with our analysis of variance test. And so in the next set of slides, we will apply that to our one-way ANOVA smoking example.